we have started a most powerful method to deal with the problem of scattering in quantum mechanics, and that was actually the method of partial waves, or you can say the partial wave analysis. Actually, that was just an introductory lecture on this concept, and we have seen that the method of partial waves is mainly applicable to spherically symmetric potential, or you can say the central potential. In fact, this method consists of the expansion of wave function as a series of spherical harmonics multiplied by a radial wave function, as you have learned in case of hydrogen atom. Okay. Actually, I have also introduced you to the spherical Bessel function in that lecture. And today you will see the utility why I have explained the brief concept of spherical Bessel function in my introductory lecture. You will see today. In fact, when you discuss the proper theory of partial wave analysis, you always need the idea of spherical Bessel function. That's why I have introduced you to the spherical Bessel function in my first introductory lecture on partial wave analysis. In fact, when you talk about the partial wave analysis, actually this method was originally applied by the well-known scientist Rayleigh to the scattering of sound waves. But later on, two famous scientists, first one is Faxen and another is Holtsmark. These two scientists actually used the idea of partial wave analysis to the scattering problem of Schrodinger equation. Okay, or you can say not Schrodinger equation but Schrodinger wave. So you can say that we are going to learn about the idea which was developed by Faxen and Holtsmark in dealing with the problem of a scattering of Schrodinger wave today. In fact, to discuss a scattering, we first show that the plane wave is equivalent to a number of spherical waves. So I have written here the expansion of plane wave. You will see that when the plane wave is expanded, then it is found that it is equivalent to the superposition of number of spherical waves. So first of all, we will explain this fact, and after that we will deal with the actual problem, which is our basic aim, to find the scattering cross section. Okay, because you know in any scattering experiment the parameter which is calculated and in terms of which every aspect of the scattering problem is dealt, that is called a scattering cross section. That is the differential scattering cross section and the total scattering cross section. So after knowing the fact that plane wave is just the sum of a large number of spherical waves, we will learn about the calculation of a scattering cross section. So now let us start to know how we can expand a plane wave and how we can show that a plane wave is just the sum of a large number of spherical waves or infinite number of spherical waves. First of all, we are going to see this. Okay, you know, when you write the Schrodinger wave equation for a free particle, when you say free particle, what does it mean? You know, for a free particle means the particle whose potential energy is zero. That is, when V of R will be zero, you can say that we are talking about a free particle. So for a free particle, what will be the Schrodinger equation in 3 dimensions? You know, this will be del square psi plus 2 mu over h bar square E psi equal to 0. And if you take k equal to plus a square root of 2 mu e over h bar square, you can write this equation in this manner. This is del square psi, that is Laplacian psi, plus k square psi equal to 0. Psi is the wave function or eigenfunction, you know. Now we consider, as we usually consider in a scattering problem, that there is a scattering center or a scattering potential, and a beam of particle is incident on it. And generally in a scattering problem, we consider that the incident beam is moving in z direction, and each particle of this beam has linear momentum h bar k, okay, because in general we consider the monoenergetic particle. So the linear momentum of each and every particle of the incident beam is taken to be same, and that is equal to h bar k. So if we consider that the particles of momenta h bar k are incident along z axis, then if you want to write the plane wave solution of this Schrodinger equation defined in equation 1, what will be that? You know, this is given as psi equal to e to the power ikz. Here the constant factor which will be multiplied to this exponential function has been taken 1 for sake of simplicity. Okay. In other words, you can also write this as e to the power I k dot r, or you know, in a spherical polar coordinate system, z is simply equal to r cos theta. So you can also say that psi is equal to e to the power I k r cos theta. And since we consider that the angle between r and this k, that is wave vector k, is theta, so r cos theta is kr cos theta is written as k dot r. Okay, so this is the plane wave solution of equation 1 defined in defined for, this is just the Schrodinger equation for a free particle. Okay, now actually due to the spherical symmetry, because when we will consider the potential in our discussion on calculation of a scattering cross section, you must take the potential spherically symmetric, or you must take central potential. And you know, the problem of central potential or spherically symmetric potential is more convenient in dealing in a spherical polar coordinate system. So let us try to write this equation 1 in a spherical polar coordinate system. I hope you have an idea of the expression for this Laplacian operator del square in a spherical polar coordinate system, because I have discussed it several times earlier in quantum mechanics, also in mathematical physics. So when you will write the expression for del square, that is Laplacian operator in the spherical polar coordinate system, then this equation 1 can be written like this. This is 1 over r squared del r, r squared times del psi by del r, plus 1 over r squared sine theta del theta sine theta del psi by del theta, and plus 1 over r squared sine squared theta del 2 psi by del phi square. Here r, theta and phi, you know, these are the spherical polar coordinates, and plus k square psi equal to 0. Okay. So this is a Schrodinger equation for a free particle written in a spherical polar coordinate system. Now actually every surface of constant phase in the plane wave is symmetrical about the direction of propagation, which we have taken in this case at z-axis. Since every surface of constant phase in the plane wave is symmetrical about the z-axis or direction of propagation, so you can say that in case of plane wave there is an azimuthal symmetry. And when you say that there is an azimuthal symmetry, it means the wave function psi is independent of the coordinate phi, which is azimuthal angle. And if psi is not phi dependent, then this derivative del 2 psi by del phi square will be 0. So taking under this fact under account that there is an azimuthal symmetry in case of plane wave, the Schrodinger equation which I have mentioned here, that will become what? We will simply drop this term containing the variable phi, and so that equation becomes 1 over r squared del r squared del psi by del r plus 1 over r squared sine theta del theta sine theta del psi by del theta plus k square psi equal to 0. You can see here actually the function psi is now a function of two independent variables r and theta, and this is a partial differential equation of second order. And you know, the most appropriate and convenient method to solve a partial differential equation of second order is the method of variable separation. So we will try to solve this equation by using the method of variable separation. And you know, when we will apply it, this solution, this psi of r theta, this is actually the solution of equation 2, that can be written as r of r times theta of theta. Here this capital R is a function of only the variable small r, and capital theta, this is a function of only the variable small theta. Now when you will use this solution psi of r theta equal to r times capital theta in this equation 2, then this equation will become like this. Actually I have not done here the algebraic steps to transform this equation in this form, because I have done similar problem earlier several times in your course on quantum mechanics. You can see my problem on the harmonic oscillator, okay, hydrogen atom. So you have used actually this fact at several places. So I have written it directly. When you will actually find the value of this del psi by del r, del psi by del theta from here and substitute in this equation 2, your result will be like this. This will be 1 over r d dr r square dr by dr plus k square r square plus 1 over capital theta of theta sine theta d d theta sine theta d theta by d theta. Actually here I have not used the partial derivative symbol, because now when you talk about the function capital R, that is only a function of a small r. This capital theta, this is only a function of a small theta. So actually the partial derivative has no specific meaning here, and we can use the ordinary derivative. So now this equation can be written as 1 over r d dr r square dr by dr plus k square equal to this much. Now see this equation 3 seriously, and when you will see it, you can see that LHS of this equation depends only on this small r, while the RHS of this equation depends only on this small theta. And you know, r and theta both are independent variables. So here variables have been separated. LHS is a function of a small r and RHS is a function of a small theta. And you know, if LHS is a function of r and RHS is a function of theta, and r and theta are independent variables, so for all values of a small r and a small theta, this equation 3 will hold only when both sides of this equation will be equal to the same constant. Okay. if they are equal to the same constant, only then this equation will hold. Okay. So you can write both sides of this equation equal to a constant, and that constant has been written in this form: L times L plus 1. Actually here L is a non-negative integer. Here actually you will see later on that this L must be 0, 1, 2, 3 and so on. Okay. So the RHS has been replaced by this constant factor L times L plus 1. Actually, we write this constant as a product of the two successive non-negative integer for convenience. Okay. L is a non-negative integer and L plus 1 are two successive non-negative integers. Okay. Now actually we will cast this equation 4 in a standard differential equation, which is actually called Legendre equation, and that can be done by considering this a new variable mu, which is equal to cos theta. And when you will take mu equal to cos theta, you can see that this sin theta will be equal to root over 1 minus mu square. Okay. And after doing some algebra, this algebra I have already done earlier in several videos of my channel in quantum mechanics. So I am not doing that algebra here. When you will try it to change this d theta in terms of this sin theta will be replaced by this, and the variable and the operator d theta will be found. And then you will see that this equation 4 changes in this form. This is 1 minus mu square d2 theta by d theta square minus 2 mu d theta by d theta plus L times L plus 1 theta of mu equal to 0. If you have watched my video on Legendre equation in the playlist Mathematical Physics, you can easily say that this equation 5 is nothing. This is simply the Legendre's differential equation. Okay. And you know, if we consider the all possible values of range of the all possible values of this mu, you know, theta varies from 0 to pi, and when theta will be 0, cos theta will be plus 1, and when theta is pi, then cos theta will be minus 1. So you can say that this mu varies from minus 1 to plus 1. Okay. Therefore, the solution of this equation 5 will be bounded between for mu equal to plus minus 1, that is theta equal to 0 and pi. And if the solutions should be bounded for these two values of mu or these two values of theta, then definitely L must be 0, 1, 2, 3 and so on. Okay. And in this condition, the well-behaved solution of this equation 5 is nothing. This is simply called Legendre's polynomial. So the solution of equation 5 is Legendre's polynomial, and that is given as theta of mu is equal to PL of mu. Here PL of mu is the Legendre polynomial. Okay. Now, as I have told you that both sides of this equation 3 must be equal to same constant, and we have considered that constant in this form L times L plus 1. So now let us equate the LHS of that very equation to that constant. So 1 over r d dr r square dr by dr plus k square r square is equal to this much. Okay. Now for convenience, I am considering rho a new variable rho related to r in this manner, rho equal to kr, so that the equation form of equation will become simpler. Although in the last of the video in our calculation, again I will replace this rho by kr. Okay. So when you will consider that r is related to this new variable rho by this relation, and when you will use this relation in this equation, that is the radial part of the Schrodinger equation, then the radial part of the Schrodinger equation becomes 1 over rho square d rho rho square dr by dr plus 1 minus L times L plus 1 by rho square r of r equal to 0. Okay. Now, as I have introduced you to the spherical Bessel function in my first video on this partial wave analysis, so definitely now you can see this equation 6, and you must recognize that this equation is simply the spherical Bessel equation. And if it is a spherical Bessel equation, what will be its solution? I have told you that the solution of this equation will be simply a spherical Bessel function denoted by the symbol j of L rho. Okay. And now if you can see that the radial part of this equation has the solution which is a spherical Bessel function, and the polar part of this equation has the solution which is Legendre polynomial. So what will be the exact solution? You can see the exact solution, that is psi of r theta of this equation 2, is simply the product of these two solutions. Okay, product of these two solutions. So the exact solution of this, or you can say the bounded solution of equation 2, then can be written as a linear combination of the product of these two solutions. Okay. And therefore, when you will take the linear combination of this, then you can write the solution psi equal to e to the power I rho mu, and that will be equal to summation L0 to infinity AL JL of rho times PL of mu. Actually here AL has been taken as the coefficient, because when you will take a linear combination, then you have to multiply the different terms after by suitable constants a1, a2, a3 and so on. Okay. And because when we take psi equal to as a linear combination of psi 1 psi 2, psi is a psi 1 plus a1 psi 1 plus a2 psi 2 plus so on. So this is actually the constant coefficient. Okay. Now in fact, after scattering, the scattered particle is far away from the scattering center. So in fact, our solution must be valid under the condition when r tends to infinity, that is called asymptotic form. So when you talk about the larger value of rho, you must have to put here the asymptotic form of the spherical Bessel function, GL of rho. And in my introductory lecture, I have already introduced you to the asymptotic form. And so you can say that JL of rho, when rho is much greater than 1, or you can say when rho tends to infinity. Both of these conditions are same. Then JL of rho becomes 1 over rho sine of rho minus L pi by 2. Okay. So this is the asymptotic form of this spherical Bessel function. Now, first of all, we will have to evaluate the value of AL. And if you want to evaluate the value of AL, what we will have to do? First of all, we will multiply both sides of this equation by Pm of mu. Okay, Pm of mu. Or you can say PL of mu. Instead of it, you can also say PL of mu. But for general value, we will consider two different subscript. Okay. And then we will integrate this equation 7 after multiplying by this Legendre polynomial for the all values of theta, which you know that ranges from 0 to pi, or the cos theta or the value of mu varies from -1 to +1. Okay, so you can see this will be what? In LHS there was e to the power rho I rho mu, and I have multiplied it by PL of mu and integrated from -1 to +1. Here the value of mu is equal to mu, you know, has been written for cos theta, and when this will be equal to -1 for theta equal to pi. Okay, and mu is equal to +1 for theta equal to 0. Okay, so the limits are -1 to +1, and in RHS there will be summation over m am jm of rho. Okay, am jm of rho, and integration from -1 to +1 PL of mu times PM of mu d mu. You can also take PL of mu, that will be mod of PL of mu square. Then here you have to put L subscript, and here also L subscript. But you can use the different subscript. Okay. Now, you know the orthogonality property of this Legendre polynomial. If you have not an idea of it, I will suggest you watch my video on Legendre polynomial, and there you will see the orthogonality property of this Legendre polynomial. Actually, when you will use the orthogonality property, actually the value of this integral is given as 2 over 2m plus 1 times delta ml. You know delta ml is Kronecker delta. Okay. And this Kronecker delta, you know, when m and l both will be equal, that is equal to 1. So taking m equal to l, now m is replaced by l, and therefore this will become 2 over 2l plus 1. Okay, and this will be 1, and al jl of rho. Okay, so now I have written this factor in RHS, in LHS, you can see. Now, the LHS of this equation, which is integral from -1 to +1 e to the power I rho mu times Legendre polynomial PL of mu. Now, we will integrate this by using the method of integration by parts. Let us take this PL of mu as the first factor or first function, and this exponential function e to the power I rho mu as the second function. You know from the formula of integration by parts, what will be this? This will be first function, that is PL of mu, times integral of second function. Integral of e to the power I rho mu, this will be what? This will be e to the power I rho mu divided by I rho. And limits are from -1 to +1. Okay. And after that we write minus integral of differential of first function. So this is this PL dash, this is differential of PL. Okay. And integral of second function. Integral of second function e to the power I rho mu will be again e to the power I rho mu divided by I rho. Okay. Now this second integral in RHS will be again integrated by using the technique of integration by parts. I have not done it. But if you will try, then you will see that when we will again take this PL dash of mu as the first function, e to the power I rho mu as the second function, then we will write first function PL dash of mu times integral of this much, and its integral will be e to the power rho mu divided by I rho. And so I rho times I rho, that will be minus rho square. So it is obvious that this second term will contain the factor 1 over rho square. So I have mentioned it here. You can see integrating the second term by parts, we get the terms proportional to 1 over rho square. I think you have understand. If you will integrate just once more, you will have the factor 1 over rho square. Okay. But we are talking about the situation which is called asymptotic form of the spherical Bessel function, and in its asymptotic form, you know, we consider this rho tending towards infinity. So when rho will tend to infinity, this 1 over rho square will tend to 0. And that's why this second term in RHS of this result will vanish if we are talking about the asymptotic form of a spherical Bessel function. So under this condition, our result will become what? This will be, you can see, 2 over 12 plus 1 times AL times, now asymptotic form of this JL of rho. You have already seen that the asymptotic form of JL of rho is this much. This is 1 over rho times sine of rho minus L pi by 2. Okay. And in RHS, there will be only now this first term. Now let us simplify this first term. 1 over I rho, it is at each, you can see. Now put the limit. When you will take mu equal to plus 1, the first term will be e to the power I rho times PL of 1. Okay. And minus, now take the lower limit minus 1. So this will be e to the power minus I rho times PL of minus 1. Okay. I hope you have an idea of Legendre polynomial. And if you have not a concrete knowledge of Legendre polynomial, I will again suggest you for watching my video on this Legendre polynomial in the playlist of mathematical physics. There you will get every aspect of it. And if you will watch that video, you will find that this PL of 1 is equal to 1 and PL of minus 1 is equal to minus 1 to the power L. Okay. And this minus 1 to the power L can be written as e to the power IL pi. Actually, why you can write this like this? Because e to the power IL pi, you know, this equals what? This is cos L pi plus I sin L pi. But you know, L is the non-negative integer. This is 0, 1, 2, 3, so on. So this term will vanish. This will be 0. So this is simply cos L pi. And cos L pi is equal to minus 1 to the power L. When you will take L equal to 0, this will be minus 1 to the power 0, that will be 1. If you will take L equal to 1, this will be cos pi, that will be minus 1. So minus 1 to the power 1 is minus 1. Okay. So minus 1 to the power L may be written as e to the power IL pi. I hope you have understand it. Now let us use these values in our result here. You can see. So using this, we find that this is 2 over 12 plus 1 times Al times 1 over rho sine rho minus L pi over 2, and that is equal to 1 over I rho, and times e to the power I rho minus e to the power minus I rho times e to the power I L pi. Now this factor inside the square bracket can be simplified in this manner. You can see. I have actually taken here e to the power I L pi by 2 as a common factor. If you will take it as a common factor, the remaining terms will be e to the power I rho minus L pi by 2 minus e to the power minus I rho minus L pi. You can check it. When you will multiply by this factor e to the power I L pi by 2 to the terms inside the square bracket, result will be same as you can see here. You can check it. But you know, e to the power I theta, okay, minus e to the power minus I theta are divided by 2i. This equals sine theta, okay, and therefore this e to the power I theta minus e to the power minus I theta, this will be 2i sine theta. 2i sine theta. Okay. So instead of this e to the power I times L minus L pi by 2, rho minus L pi by 2, minus e to the power minus I rho minus L pi by 2. Here at the place of theta there is rho minus L pi by 2. So instead of it we can write 2i times sine this much, but I in numerator will cancel out by the I in denominator, and so this result is 2 over rho times e to the power I L pi by 2 times this much. Now you can see this 1 over rho will cancel, sine of rho minus L pi by 2, this will also cancel, okay, and here this factor 2 will also cancel. Therefore our result is AL over 2L plus 1, and that will be equal to e to the power I L pi by 2. Okay. In fact, what will be this e to the power I L pi by 2? You can see e to the power I L pi over 2. This is cos L pi by 2 and plus I sine L pi by 2. Okay. As you know, this L is a non-negative integer. Okay. And when you will take L equal to 0, this will be sine 0, which is 0. When you will take 1, sine, this will be sine pi by 2, that will be I. Okay. So in this way, when you will actually obtain its value, you will see that its value is equal to I to the power L. I to the power L. Okay. And that's why AL is equal to 2L plus 1 times I to the power L. Okay. So in this way, we have obtained the value of the coefficient AL. Okay. So after obtaining it, let us substitute the value of AL in the equation number 7. You can see this is your equation 7. At the place of AL, now we will substitute that value. And so we will get the value of this plane wave psi equal to e to the power I rho mu. Okay. And so after substituting, we get psi equal to e to the power ikz, and that will be equal to summation L0 to infinity I to the power L times 12 plus 1 JL of rho a PL of mu. Now instead of mu I have written cos theta. Actually this is a very important equation and this is called Bauer's formula. Bauer's formula. In fact, this result actually shows that the plane wave is equivalent to the superposition of a number of spherical waves. Actually, this JL of rho, this is the solution of a spherical Bessel function. It represents the spherical waves, and that's why this equation implies that the plane wave is equivalent to the superposition of infinite number of spherical waves. And as I have told you earlier in the beginning of this lecture, that the first part of this lecture is intended for it. I have to prove that the plane wave is just equivalent to the superposition of number of spherical waves. And in this way, we have proved it. But our prime aim is to discuss the scattering problem. And if you are now intended to deal with the problem of scattering, then again you have to write the asymptotic form of this JL of rho. As you have seen earlier that this JL of rho in asymptotic form can be written as 1 over 2I rho times e to the power I rho minus L pi by 2 minus e to the power minus I rho minus L pi by. Here actually this factor 2 has been taken for convenience. Okay. And when you will simplify it, as already I have simplified, so I am writing it here, this can be written as I to the power minus L over 2I rho times e to the power I rho minus 1 to the power L e to the power minus I rho. Okay. After getting the asymptotic form of this JL of rho in this form, let us now substitute this value of JL of rho in this Bauer's formula at the place of JL of rho, so that we will get the asymptotic form of this wave function psi or e to the power ikz or e to the power ikr cos theta. Okay. So after substituting it in this equation, you can see our result will be what? This will be summation over L 2L plus 1 over 2IKR times e to the power IKR minus 1 to the power L e to the power minus IKR PL of cos theta. Okay, you can check it. You can check the algebra. In fact, here I have replaced this rho by KR for convenience. As I have told you earlier in my video that for convenience I have taken KR equal to rho. Now for getting the final result I am using the actual value of rho which is equal to KR. Okay. Now for a spherically symmetric potential, what is the Schrodinger equation? You know, for a spherically symmetric potential, the Schrodinger wave equation is written as del square plus k square minus u of r psi of r equal to 0. Here actually this u of r is the effective potential which is given by 2 mu v of r by h bar square. Okay. Now the solution of this equation, if you consider the azimuthal symmetry, in case of azimuthal symmetry, the solution of this equation is written like this. This is psi of r equal to summation over L 2L over k times I to the power L UL of R over R PL of cos theta. Okay. Actually here this factor 2L plus 1 times I to the power L has been taken for convenience, because in the expression for the asymptotic form of GL of KR, you have seen this factor comes. So this has been taken for convenience. Okay. Now actually this equation 11 will be correct only when this UL of R satisfy this Schrodinger equation. I have actually introduced you this when we have actually discussed the Green's function for this operator. I have introduced it. Okay. Now let us substitute this equation 11 into this equation 12. After substituting this in this equation, our result will be d2 ul by dr square plus k square minus u of r minus L times L plus 1 over R square UL of R equal to 0. Actually here I have not done the algebra, because this algebra has been already done when I have discussed the Green's function for this operator del S square plus k square. So I have written it directly here, so you may remember it. Now actually, as I have told you in the introductory lecture, that this method is applicable for a central potential which must be of short range. So definitely the scattering potential should be taken of short range. And when you say that the potential is of short range, how we can write the mathematical condition for it? That condition will be written as limit r tends to infinity, r times v of r must be equal to 0. So this is the case of short range force or short range potential. So for a short range potential or short range force for which this condition holds, then the asymptotic form of UL of R will be e to the power plus minus IKR. Okay, and that's why in this condition UL of R when R tends to infinity is given like this. This is AL e to the power IKR plus BL e to the power minus IKR. Okay, and this can be written in the terms of sine function, in terms of cosine function, you know. Okay, and so instead of this you may write CL times sine of KR minus L pi by 2 plus delta L. Actually here you know this factor L pi over 2 comes when we talk about the asymptotic form of the Bessel function. So here L pi by 2 has been introduced for the sake of convenience. And this quantity delta L is what? This is a very important quantity. This is actually called phase shifts. How much, due to the scattering potential, the phase of the scattered wave has been changed from the incident wave, that is measured in terms of delta. This is a very important quantity. Now actually we find that this V, when V of R is equal to 0 everywhere, then this UL of R must be equal to KR times JL of KR. Okay, and you know its asymptotic form will be sine of KR minus L pi by 2. Therefore this delta L, which are actually phase shifts, definitely this has been introduced by the scattering potential. Okay, now this equation 15 can be written in this manner. UL can be almost equal to 1 over 2y CL times minus I to the power L times e to the power I delta L e to the power ikr minus 1 to the power l e to the power minus I delta l e to the power minus ikr. Actually here I have used the idea which we have just discussed earlier. Okay, so I have written it directly here. Now this equation 16 which we have obtained here, let us use this equation 16 in your equation number 11. See, this is your equation 11, and here the value of this UL of R will be substituted, which we have defined in that equation 16. So I will not turn the page. You can do it in your notebook, and when you will do, then you will see that this psi of R when R tends to infinity can be written as summation over L 2L plus 1 over 2I kr. Kr is for rho times Cl times e to the power I delta times e to the power ikr minus 1 to the power L e to the power minus I delta times e to the power minus ikr times PL of cos theta. Okay, so in this way we have obtained the complete wave function. Now you know in a scattering problem, actually this psi of R is written as e to the power ikz plus f of theta times e to the power ikr over R. I hope you can remember this result, because when I have discussed the scattering amplitude and cross section in my first and second video, then we have seen this. Okay. Now in this result we will use our equation number 10. So let us see what is in equation 10. This is your equation 10. See here, and here this psi of psi, which is e to the power ikz, has been defined. So after using this equation 10 in this equation of scattering, this psi of R will be now given as summation over L 2L plus 1 over 2I kr PL of cos theta times this much plus f of theta e to the power ikr over R. Okay. Now actually we have defined the same quantity psi of R two times. The equation 18 on the basis of scattering theory, and this equation 17. But both psi of R are same quantity, so definitely the coefficient of e to the power ikr and e to the power minus ikr in both of these equations must be identical. So now let us equate the coefficients of e to the power ikr and e to the power minus ikr. When you will equate it, I am not turning the page, you will see that Cl will be equal to e to the power I delta L. So this unknown Cl depends on the phase shift. Okay, and the f of theta, this will be equal to this much. You can check. This is summation L0 to infinity 12 plus 1 e to the power 2I delta minus 1 over 2ik times PL of cos theta. Now let us simplify the RHS of this equation a little bit. So this is summation L0 to infinity 2L over 12 plus 1 over k times. Now I have taken here e to the power I delta as a common factor. Okay, and then there will be e to the power I delta minus e to the power minus I delta L. When you will multiply by this outside factor to the terms inside the bracket, you will get the same result, e to the power 2I delta minus 1. You can check it. And divided by 2I, there here is 2ik, k is here, and 2I has been written here. And this is PL of cos theta. But you know that this is sine delta L. This is sine delta L. So f of theta, which is actually the scattering amplitude, okay, that is equal to summation L0 to infinity 12 plus 1 over k times e to the power I delta sine delta L times PL of cos theta. So in this way we have obtained a very important quantity which is called scattering length. Okay, and you know that the differential scattering cross section is simply equal to the square of the modulus of this f of theta. Okay, so the differential scattering cross section, which is sigma of theta, that will be equal to a square of modulus of this equation 19, and so it can be written as 1 over k square, a square of the modulus of summation L0 to infinity 12 plus 1 PL of cos theta e to the power I delta L sine delta L. But when you will take mod e to the power I delta L square, that will be e to the power I delta L times e to the power minus I delta L. This is complex conjugate of it, and that will be equal to 1. Okay. So a square of the modulus of this exponential factor will be 1, and that's why you may drop it from here, this e to the power I delta L. Okay, that will be equal to 1. Now after getting the expression for the differential scattering cross section, we can easily find what will be the expression for the total scattering cross section, because you know the total scattering cross section is the integral of the differential scattering cross section. So this sigma, which represents the total scattering cross section, that is equal to integral of mod of f theta square d omega. Okay, but d omega, this denotes the solid angle, that will be equal to 2 pi sine theta d theta, and therefore this is 2 pi, which is constant outside of the integral, 0 to pi sigma theta sine theta d theta. Okay, and because mod square of the modulus of f of theta is equal to sigma theta. Okay, now let us substitute the value of this sigma theta from equation A1 here, and after substituting it you will see that this is 2 pi over k square integral summation L0 to infinity 12 plus 1 whole square sine square delta L, because I have told you that this e to the power I delta L, mod of e to the power I delta L square, that is equal to 1. Okay, and the remaining factor is mod of PL of cos theta square sine theta d theta. Okay, so you can see this is 2 pi over k square summation L0 to infinity this much, and integral from 0 to pi PL of cos theta square sine theta d theta. But again you know that from the orthogonality property of Legendre polynomial, that this integral is equal to 2 over 2L plus 1. Okay, 2 over 2L plus 1, and therefore 1 of this 2L plus 1 will cancel out, and sigma will be equal to this much. This is actually sorry, just for a minute the page has been turned, but this will be okay. So this is the expression for the total scattering cross section. Actually here this delta L is the phase shift of the Lth partial wave and is unknown parameter, and this will be evaluated. So in our forthcoming lecture we will see some of the techniques to evaluate this delta L, which is the phase shift of the Lth partial wave. Okay, so I think you have clearly understand the idea of calculation of a scattering cross section by the method of partial wave analysis. Okay, thank you very much.